Continuity conditions for intervals. Suppose we have a function f of x on the closed interval from a to b. We say that the function is continuous on this closed interval from a to b if it passes the first three conditions of continuity that we've been going over on the open interval from a to b, and at the left endpoint, the limit of f of x as x approaches a from the right is equal to f of a, and at the right endpoint, the limit of f of x as x approaches b from the left is equal to the function value at b. Similarly, we could have a function f of x on the interval that's closed at a, but then open at b. And we say that the function is continuous on this interval that's closed at a but open at b if it passes the first three conditions of continuity on the open interval from a to b, and at that left endpoint, the limit of f of x as x approaches a from the right is equal to f of a. Notice that we did not need to include the requirement for the right endpoint since the interval is not including it. The reverse could also occur. We could have a function f of x on the interval that is open at a, but closed at the right endpoint b. And we say the function is continuous on the interval that is open at a and closed at b if it passes the first three conditions of continuity on the open interval from a to b, and at the right endpoint, the limit of f of x as x approaches b from the left-hand side is equal to f of b. Notice that we did not need to include the requirement for the left endpoint since the interval here is not including it. Let's try this example for continuity at an endpoint. Determine the continuity of f of x, which is equal to 1 divided by the quantity x minus 2 on the interval that's open on both sides from -5 to 2. Let's see what happens. To begin, we need to determine if the function value at c exists, the limit of f of x as x approaches c exists, and the limit of f of x as x approaches c is equal to the function value at c for all values of c in the given interval. So does f of c, or the function value of c, exist for all c values within the interval, open interval that is, from -5 to 2? So they do not include the endpoints. Well, f of x is continuous and is only undefined when x equals +2, and you would get a 0 in this denominator. Since this value of +2 is not included in the interval, the open interval from -5 to 2, f of x is continuous. Does the limit of f of x as x approaches c exist for all c values in the given interval? Well, we have our function f of x being 1 divided by the quantity x minus 2, and +2 is not being included in this interval. So similar to the last question, this limit does exist for all c values within the given interval from -5 to 2. Remember that x equals 2 is not included. If I was to put in x equals 1, I would get 1 divided by 1 minus 2, which is -1, so I would get a -1 value. If I substitute 0 in, I would get -1/2. If I did -1, I would get -1/3. Like, I'm still getting all of the required values within this interval. Does the limit of f of x as x approaches c equal the function value at c? Does that exist for all c values within the given interval that we have? Well, we know that for all c values in our interval that the limit of 1 divided by x minus 2 as x approaches c would be equal to 1 over c minus 2. And whether I put -4 in there and get -1/6, or -3 in there and get -1/5, that limit is going to exist and be continuous and equal the function value within all of the x values given in this interval. So we can conclude that f of x is continuous on the open interval from -5 to +2. The question was changed slightly. What if it was written like this? Determine the continuity of f of x equaling 1 divided by x minus 2 on the interval that's closed at -5 and open at +2. Well, we already know from the work that we did prior that our function is continuous on the open interval from -5 to +2. But now we have this closed bracket at -5. So what we need to do is we need to determine the limit of 1 over x minus 2 as x approaches -5 from the right. Well, if we can use direct substitution in here, and when we do that, we will get -1/7. And it does equal the function value f of -5. And then since the limit of f of x as x approaches a from the right equals the function value at a, f of x is continuous on the interval that is closed at -5 and open at +2. What if the question was changed again? Determine the continuity of f of x being equal to 1 divided by the quantity x minus 2 on the interval that's closed on both sides from -5 to +2. Continuity on closed intervals is determining whether or not it's continuous on the open interval from -5 to +2. Well, we've already proven that, so this is definitely fulfilled. Then we have to examine the left endpoint. Is the limit of 1 divided by x minus 2 as x approaches -5 from the right, is that equal to the function value at -5? Well, the limit is equal to -1/7, which we found, and that's also equal to the function value. If you substitute -5 directly in there, you will get -1/7. Now we also have to look at +2. So now we have to take the limit of 1 divided by x minus 2 as x approaches 2 from the left, and that's actually approaching -infinity. So the limit as x approaches 2 from the left is -infinity, and the function value at 2, you would get 2 minus 2, which is 0. It does not exist, it's undefined. So therefore, f of x is not continuous on this closed interval on both sides from -5 to +2.